Okay, we will wait for the students for 3 to 5 minutes so that they join us, and then we'll start. Uh, yeah. Okay, we'll start now. Uh, Let me share my screen. So, uh, in the videos which followed, we had the Euler equation, where detailed derivation of the Euler equation is done. And before that, something about equation of continuity was discussed. And equation of continuity, which is just this. The Euler equation, which is just given by the last Euler equation, which is just given by this. And then we discuss something about Bernoulli's law. And then something about transport of momentum and all this thing, which is which comes in Navier-Stokes equation. And Stokes drags. So let us first start with the Euler equation only. So I mean the first video. So the equation of continuity was derived by first assuming that the defining the density of particles as this, which is sum over all the particles, Dirac delta of position minus the position of the ith particle, which say follows some trajectory. And the current is defined as from here we get from here we can see that now the first question is show this satisfies the continuity equation. The way to do it is we know that the continuity equation is uh, d rho dt at j equals 0. So first we'll calculate d rho dt, which is summation over I equal to 1 to n ddt of Dirac delta. What we want to do now is write this in terms of j, in terms of the positions. If I want to bring a grad here, So what I will do is I'll use the chain rule. J from 1 to say k. Suppose this is in k dimension. Then I'm going to write drk by dt dot. So this is nothing but the velocity, which is this is multiplied. There's no dot here. But if I want to write it in vector terms, I'll have to write r vector dot times this is nothing but gradient of Dirac delta. So we'll get this. And now if we evaluate L of j, we'll have we have bi, which is nothing but if we write this in vector terms, so this is nothing but vector dot only. Now uh, the gradient will only work. The gradient will only the gradient will be acting on these Ris. So we'll have gradient of Dirac delta r vector and I vector t. Since there's a minus sign here, I will get an overall minus sign. Therefore, when we add a plus b, we will get 0, and a plus b is nothing but the continuity equation. So we showed that this satisfies the continuity equation. Sorry, there's this. Hmm. But, oh, sorry, there's a minus sign is here. It's not here. The gradient, sorry, so the mistake is the gradient is with respect to r here. And when I'm doing this, I'm actually doing chain rule in this case. I'm differentiating this, and then I'm differentiating the uh, Ri parts. So I'll get um, sum over Ri, and it will look like this. So we'll get something like this. So the minus sign is because of that. So there's other way. We now will test. There's other way of showing continuity, and these are using the Poisson brackets. So we'll see. We'll try to show. The second question is we'll have to show with the Poisson bracket between this and 0. The equal time Poisson bracket with different r's. This is 0. So we have summation ij, just plugging in the values of this thing. Dirac delta r minus RIT Dirac delta r prime minus r j t, which implies summation over ij. When you take, there is no momenta here. So there's only suppose the Poisson bracket is with respect to r. So you are going to take summation over Dirac delta, summation over r. The other part which has this, it will make this Dirac delta go away. Similarly in the minus part. So since there is no p variable, this is equal to 0. So that's how we do it. Now we calculate the Poisson bracket between evaluate So the way to evaluate is again we are going to put this thing. So uh, this is nothing but there is a sum over k in this part and j from the other part, and we have the Dirac delta r minus r k t r and j l. So I'll write, since there is v here, that can be written as p, and we are going to consider p to be uh, m v dot. So, sorry, mv, so mr dot. So that is why I'll put this. So we'll have an overall factor of 1 by m minus now 0 dr dot, this is 0. So we'll have only the first term. So we have something like m. Okay, let me just write this as root 4 now. So we'll have this is it. Now we'll calculate d rho and yeah. So now we'll calculate, there's a summation here for these index. D rho dri can be written as sum over K dri Dirac delta r minus r k t, these are vectors, and this can be written as uh, so using chain rule, what you're going to do is we are going to write this term in terms of a gradient. So that is possible. Yeah, something like this. So gradient of Ri. So gradient Ri means that so let me just take it gradient of R and with x over the Dirac delta. Now, when you differentiate this, we want only the ith to survive. So what we are going to write is, suppose this R has a lot of components. Only that component will survive, which is I in it, because then the other derivative, the that will be, say the other components are say R L R I. So if we want only that component which where L is equal to I that survives, then we should write this to be along with the Dirac Kronecker delta of L equal to I and to I, and there will be a minus sign because the derivative is acting on this one, and there is a minus sign in front. So it is actually, this thing is actually just minus of this thing. It's like we are just doing chain rule. We are differentiating this first and differentiating what is inside. When you differentiate what is inside, we have to differentiate this part, and that will just give us Dirac delta, Kronecker delta. So yeah. And so if we put it there in the uh, in the this thing, in the yeah. One more thing, since we are looking at the L component, so there should be one more symbol which we want to say this is the Lth element of this. Now, when we look at this thing, we have 1 by n sum over I from 1 to n. This is the first part. Times PIL, which is nothing but R dot. And we'll have this and there, because if I change this to P and I'm changing the upper one to P also, those n cancels and there's only one n answer. So I will have something like I will be left with r prime minus RIP. This will just give me I equal to L, or and we'll get we evaluated this, and we'll have I from 1 to n Dirac delta R L uh, derivative, sorry, gradient of RL. Like we are looking at the RL component. The Kronecker delta makes this I equal to L. Sorry, yeah, no, K equal to I. And we have from this part this thing. Now we can put this here and we'll get R minus, say I'll write this to be um, uh, now we are going to use the property of Dirac delta actually. If I substitute this as R prime, then also I'm fine, right? Because there's this Dirac delta which says that R prime is equal to this. So if I can so safely substitute R prime here. If I do that, I can bring that out of the summation, and I will have a summation only over this part, which is nothing but rho of R prime t. So we'll get this thing. Let me go through it once again. So when I take this thing, when I take so I have the Lth component of the current here, and I want to evaluate the Poisson bracket between rho and JL. So we know Poisson bracket is evaluated as this. And for the sake of being clear, let me not just put this here now. I'll later. I'll evaluate that later. Let me write how we write Poisson bracket. So from the definition of Poisson brackets, I'll have this thing here. So um, uh, hmm. Okay, so L is for the index of the, we want to mean that L is the index for this thing. We could have dropped L here and we'll get nothing but Kronecker deltas. Okay. So JL means that we are taking the sum over, we are taking J is nothing but VI dot gradient of something, right? So gradient of Dirac delta. There we are going to get, sorry, J is nothing but Vi times Dirac delta. So this is nothing but the Lth component of Vi. So this JL is nothing but VL, which is VL times Dirac delta, which we are going to write as PL by M Dirac delta. So yeah, so we have in that thing PL Dirac delta, and we've added this I just to uh, make it consistent with this index, which is the Dirac delta index. So Dirac delta of R vector minus Ri vector, it's like there are a lot of Dirac deltas there inside. Like it is a notation for all the Dirac deltas. Like that is like D Dirac delta x minus xi of t and y minus yi of t, something like that. Dirac delta of y minus y of t. Everything is there. So the notation for that is we are writing it together. Okay. So yeah, so I is for the index inside, and this is for the LF component. So yeah. Okay. So the third thing now which we'll look at is the commutation relation between currents and currents. Say, see, evaluate JA R vector comma T, JB R vector comma T. Let's do it with our notations. Now, JA R vector comma T actually means that we have so these are the summation over I. So let me not just put A here for now. So I from 1 to N, Bi of T, this is a vector, Dirac delta of R vector. I think this will make your, if you're confused with the notation, this will make it clear. So say there are like N particles and they have mass n, right? This I is the summation for these N particles. Now we want to look at all the N particles only, but only one component of their velocities. So if we want to look at a component of this current, this sum over I from 1 to N is going to be there. But the velocity component of I have to look at the eighth component. Say it's like x component of velocity or in the x direction. Suppose A is like say the x direction. So velocity of all the ith particles in x direction. Right? And this will be unchanged because the vector here is only this part. So this is what it would mean, and which we are going to write it as EIA by M, because uh, every particle have the same mass. If they had different masses, then we also had to give an index of like say Mi. That would mean that different particles have different masses. Okay. Now we have this I is equal to 1 to n. Now we are going to put this in the uh, Poisson bracket, and we are going to see that JAR is actually going to come out something like this. Summation I from 1 to n, summation j from 1 to n PIA by M Dirac delta R vector minus Ri vector of T, comma PJA M Dirac delta R vector minus Rj vector of T. Now, when we do the Poisson bracket, so we will have something like, so Ij means I'm clumping these two and writing this as Ij. Poisson bracket, and there's also 1 by M square. So I'll write this way. So this will be Dirac delta of. Now we want to expand the Poisson bracket, and the Poisson bracket is uh, in say 3 dimensions. That would mean A goes from 1 to, say we have a, so suppose this is in 3 dimensions, then there are 3 currents because there is A can be 1, 2, 3, X, Y, Z. So we have to, so when we do the Poisson bracket, if you remember, if you have something like AB, then we sum over all the uh, dimensions there is. I equal to say 1. Suppose you are doing this in D dimension, so you'll have uh, dA by dQi, dB by dPi minus A and B interchange. So this is how it's going to be. So we need, when we expand the Poisson bracket, we want to sum over these. Uh, we want to sum over these things too, and we'll have to give a new index for it, not A, uh, because A is already a fixed index here. It can be like, say, A and B here are like, say, X and Y, something like that. So, but in the Poisson bracket expansion, if you're doing in say any, say 3 dimension, you have to take a different sum over these things, and that sum will, that index will remain in the below part, the the operator part, actually, d by dpi or something like this. So I'll have something like ij, which is the club, which is the notation for this thing. And then I'll have a summation, say L, which goes from 1 to 3. And I'll write this, which is del by del QL. For us, it's RL. And then we have just a second. Like that. So that is del by del RL, and del by del RL of PIA Dirac delta of R minus R vector I of T, and PL JB Dirac delta of R vector minus and with the minus sign, Now we are going to exchange this RL and PL. So the first thing that might seem problematic is that uh, your the index which is below has only one index here, but the index above has two indices. To make this consistent, what we are going to write is we are going to write we are going to write an I there. This is just for the sake of this is just for the sake of being consistent. So this L actually corresponds to this index, B index, because L corresponds to dimension. This is corresponding to A index here. And the index before that, which like says about which particle is it, that is not mentioned in the Poisson bracket operators, right? So to incorporate that, we'll put one more new index, I, J, K. L is from 1 to 3, or actually the K index should have been incorporated in the Poisson bracket because this scenario, what I have written, this is for one particle in 3 dimensions or like D dimension. If you have n particle, then what you're going to have is like you can put two indexes there, the operator itself. So I'm just incorporating this. I'm doing it slowly, step by step, so that there is no confusion. So with that in mind, when we differentiate this part, when you differentiate this part, uh, this is going to act on only this. So yeah, I have been forgetting on the answer. So this part will differentiate with this part. So we'll have I, J, K, and sum over L from 1 to 3. So PIA remains as it is. And this part will take, you'll have a Dirac delta, which, sorry, you'll have the gradient which acts on there, gradient of R, and we do not denote it like which particle it is, right? So so this for the kth particle in uh, Lth derivative. That is like, this is like, say L is 3, and this is like dz, this thing. But this is for the kth particle. And now Dirac delta vector minus Ri vector of t. Now this Dirac delta itself is a shorthand notation for Dirac delta of Rx minus Rx for the ith particle t. Okay, Dirac delta of Ry minus Ry ith t. And Dirac delta of Rz minus Rz I of t. And this is sum over I, which is the particle, which is there. So, bearing this in mind, when I write this KL, I don't, I'm just concerned, when I take the derivative, I'm just concerned about, not which particle this is actually. So what I mean to say is that when you are going to differentiate this, you will differentiate what's inside also. When you differentiate what's inside, you're going to differentiate this part, RKL, and this R is only for uh, the uh, say this is for the so so this RKL, it differentiates, it is going to differentiate for the Lth component, right? Suppose this Lth component remains. This is going to differentiate for the Lth component, and then when you when you take the derivative inside whatever there is inside, so you are going to take derivative like this. Going to take the derivative in this way. Uh, Sorry, I lost my. Yeah, minus. So say the this is the pth component, and p is any one of this, minus p for the ith particle p. So when you take the derivative, you're going to differentiate this, and you are going to get a Dirac delta over. You're going to get a Dirac delta over. Oh, sorry, this should be INT. This for the particle. Yeah. You're going to get the Dirac delta over only L and P. Okay. And the reason is because the Dirac delta should only be for Dirac delta should be there for L and P, and the Dirac delta also should be there for K and I, because you are doing for the kth particle here. We're looking at the kth particle. When this I is equal to K, then only this will remain, right? So you'll have two Dirac deltas here after you apply the chain rule. So you will have Dirac delta of K with I, and we are not going to write for L, because you see this is summed over, and then what this means is just uh, what this means is just what this means is just you're going to have some uh, you're going to have something for you're just going to, so there is no free p index here. That is what I mean to say. So you may as well take this to be L itself. So if you take this to be L itself in this thing, Dirac delta, it's just one. Or in other words, if you substitute this L as P, you're not going to have anything, but this summation will break into P, and then you're going to do for every L, right? So P itself will take P from 1 to 3. So even if you don't write this, you will get the evaluate to the same result. So even if we write this, even if we don't write this, it's all right. So what this means is that when you are doing the sum over L, and P is say L, and P can be anything. Actually, if I were to do this, so let me explain it properly again. So when I take the chain rule, I have to do this thing, R terms of KL, R vector for P minus Ri of P P, but this I should do for every P, right? Because P is all the dimensions. So when I do this, I'll have Dirac delta of KL, Dirac delta of P, Dirac delta of KI, PL, sum over P, and this is just going to give me L itself, the Dirac delta of KI. And this is when this is going to get to 1, you're going to get this thing itself. Okay, so it doesn't matter if you, so if you, it doesn't matter if you write this family. So you have this part, and now you're going to differentiate this part, and this part is just, and this part is just Dirac delta of Kj and Dirac delta of Lb. And this part won't contribute, it will remain as it is. Dirac delta R minus R square. Similarly, with these changed, you're going to have this part and this part has changed. So you will have something like uh, Dirac delta Ki, Dirac delta Kj. So if you want to interchange this with this, I and J should be interchanged. LB will be changed to Dirac delta of LA, and this thing will be changed to KL. This will be R vector minus RJ. P is being differentiated. This will be R vector minus R T. So that's it. And you have a PJB. With this expression, at hand, we will just now we'll simplify this. We'll take everything away. Then KL will have, this will have, so K is equal to I and K is equal to J. So this means I equal to J. And so we will have K, we will have summation L from 1 to 3, Pi, okay, I equals to J. So Pj A. So K is equal to I. So in the summation, you'll have K equal to I. So one of the summation goes away. So suppose we keep K as it is and let K go, let I go, summation over I. And we'll have here KA, KL and all these things. But if we put summation over, sorry, I should write it. So summation K over I. So, so what I mean to say is you are going to have KA here because you have Dirac delta Kij with a Ki with a Kj. Then what you are doing is when K is equal to I, let's just look at Ki summation. Whenever K is equal to I, then only this is non-zero. So this becomes sum over say Kj, Dirac delta Kj. Whenever K is equal to J, then only this is non-zero. That means you will have sum over K only remaining. Alright. So I did that only, and whenever you had I
you substitute that with k, and whenever you will have j, you substitute that with minus ri, and I is substituted with kt. Now we are going to put this Dirac delta of LB, and when I do that, I'll have only the bth component. Whenever L is equal to B, then only this thing is possible. So wherever I had L, I have to change that to B. And this summation over this will go away. And delta of R vector minus RKT. Minus similar here, PJB. So J goes to K, KB, KB, and this RL, RKL becomes RKB, delta of R vector minus RKT, delta of R vector minus I becomes K, so in the end, we have summation over K. This part is gone, and if we put this part inside with the M, so we have 1 by M, 1 by M. Oh, okay. I missed a minus sign while differentiating this thing. While differentiating this thing, the derivative is taken with this thing, right? So wherever I was showing this, I will have a minus sign with plus sign here, because minus is here. When I am differentiating, I am differentiating it to this. So 1 by M, this pKa is just pKa along with this uh, this part with a 1 by M is nothing but JA, the summation taken inside. So JA, this R KB, KB, Dirac delta of R. There's a problem. So now yeah. So that is just J, but there is a sign over, there is a summation over K as well. So what I'm going to do is, I will, instead of this, I'm going to write some R prime, and I will write this as R prime. Okay. Then what I can do is, I can take the summation, this part out. So Dirac delta of RKB, sorry, gradient of RKB, Dirac delta of R minus R prime. And this is taken out. Now, since this is taken out, and this is R prime, this, now the summation will go inside and act on only these two and give us JA R prime T. Okay. Now there was an overall minus sign which I was talking about. So that will give a minus sign. Plus I will do the same thing here. I will have JB R prime T uh, gradient of R KB Dirac delta of R vector minus R prime. So the problem is, yeah, this is the solution, but you see, there is still one problem. When I had taken the summation inside and taken this RK, this R prime, I also have to change this, right? because otherwise the summation over R should be there. So if you leave that, you will have over D. So this is actually the final solution. The Poisson bracket of J with J. And this acts on the. Okay, nice. Now, this there is the definition of J. The definition of J. This with some manipulation can also be written. Say V is the same for all particles. Okay. If V is the same for odd particles, this is nothing but V vector. You can drop the ith index. V vector dot V vector times summation 1 over n of this thing, which is nothing but rho. So J can be written as J can be written as V vector times rho. Now, if this, what does it mean that um, V vector, all the particles have same velocity? That means we want to define velocity as not as the as not for individual particles, but as a function of r. What I mean to say from this is, let me just yeah. What I mean to say is that if you have if you have if suppose this is your space and I want to describe velocity as a function of position and time. So forget time for now. Just look at position. So if any particle comes to this position, it is going to have v of rt at some time, say a fixed amount of time. Suppose this is the first particle. If it comes here, it's going to have v of rt. Okay. If it is the second particle, it's also going to have v of rt if it comes to this position. That with that logic, at an instant r, at a position rt, if you have a say particle, you can take this out. It's the idea is that all the particles have same velocity at some position r. Okay. So instead of vit, we are we substitute uh, velocity as a function of the fields, the space. Now, if that is the case, we want to evaluate Poisson brackets of. We want to evaluate Poisson bracket between this rho and G. And we are going to use the older this is sorry, R prime. R prime. We are using the what do you say? We will take help of the older Poisson brackets, which you know. We take the results from there. Yeah. Now this can be written as this. this is 0, which we calculated earlier, minus rho. Now this part is just P, and from what you had done earlier, we have not exactly calculated this, but the way to do that is also similar. You take this, oh sorry, uh, yeah, you look at this, and you are actually going to get this only, but this row won't be there. Let me just quickly derive it for you. I'll put this as, so I'll take a component of V and I will do this. So component of V, so I will have L component of T and L del R T L del V. So V can be written as T by T by del T T so I can remove T from del sorry, del T well, this is 0 anyways. So we have only this part. And then some one, two, three. Row by row is there are row is okay. The I was taken out. Row is some but I and this is PAPL is there. With you get a minus sign from differentiating this, and you will get a direct delta of uh, T is equal to R. And you will get this R K integral delta R vector minus R. So when you do that, you will get 1 by M. This will be just sum over K, the minus sign, and over K, sum over A, 1 over 3. When you do this, you will get the direct delta R K L is A. Then R K L is A. So R K A direct delta R vector minus R K T. Yeah, so that is it. It's like mistake. Oh, yeah, yeah, that's a problem. There is slight mistake because B has an argument of R prime, and if this is at R, and if this is at R prime, you should have one more bit at the ground. Now it is correct. Without the ground, all elements are. So you're going to have, you can put an R prime here, you can put an R prime here, and you can put RK there, and you're going to find a row. So you have here the random minus R prime is there. Is equal to minus and summation over K divided delta R. Now I want to bring this out, make this R. So that can be done using R, and this is A, divided delta of R vector minus R prime, and sum over K, divided delta of R vector. So I'm just interchanging this because they will the same thing. If I were to interchange this, Dirac delta R is this thing, so they will mean the same thing. So now if I interchange this, this can be put inside and this can be written. And this is nothing but rho. This is nothing but rho. Rho at R T. So that we got that minus rho at minus rho at minus rho with R prime comma T is equal to rho and T R prime comma T is equal to minus M. Now this was VA, so we had this thing. If I were to put it for every velocity, then I'll have the R vector. So rho, now R is equal to R prime. So R is equal to RK. If I had changed some notation, if I had made this R prime and this to be R, I could have written this R prime minus this thing. And I could have written something else. It's just juggling notation. I can always make this RT. And from here, I'll find that this is equal to Just R. So if I had written this as say R R minus direct delta of R minus uh, R prime and this RK, and if I were to interchange this RK and R prime, then I'll get this, and I'll have an R here. But I will the same this thing to change. So I should have add R prime here. So that means hmm, this is correct. Okay, I have the arguments now, which I just have to put. This is correct. This is all right. This is also all right. So actually, this R can be any in this thing. So this is kind of like a dummy variable in the sense that there is Dirac delta on R minus R prime. This could as well, actually, this should have been R and this could have been some Q prime or something like that, or some Q. In that case, this is just some R minus Q or R minus R prime is itself fine. And so we can always put any variable here. That is what I mean to say. So if I put that, there is always R minus Q, say. This is at, okay, this is at R prime, that is for sure. This is at some R or Q. So Dirac delta of R prime minus R. So this can be done. And we will get this thing. Let me just check if what I'm saying is right. So here it is fine. Dirac delta of this thing is this. And we get a minus differentiate in this. And so we get, and we get this. And then we get this. Now I'm putting this here. Okay, if I had R prime minus Q, so I would put R prime here and get Q to be R. But the arguments will seem to come out. This is going to give me this. But I can always change this equation. I can always do this thing. direct delta of R prime A. So I'm renaming R and R prime. This R is R prime minus R. Since this is even, it doesn't change anything. I can always write this to be R minus R prime. Rho on R prime from T. And then I'll put this side, and then I can to take this, and then I can cancel. So even if I do the differentiation with respect to R or R prime, the result here is going to be the same because this is an even function. Yeah. So let's just verify this. Dx cos x minus y minus x minus y and then dy is x minus y. It should have here and the outline here. Good. This is correct. This is going to be the result. So if I put this up, so was of y minus x of y, it's always going to be this number. So y minus x. Sorry. So here, so we should have had something like this, which is dy of cos y minus x, which is going to be this. This is the renaming of variables. So it's like y going to x. But in this case, if you see, I have something like d dx now, cos x minus y minus sin x minus y. And we'll do y of cos x. And we'll do y minus x. X. So basically, that's what I'm doing here. Right? I'm interchanging this r minus r prime, and I had r prime here. So let me take this to be r prime, r prime. Then I will have something like well, this is what it is, y minus x is sine of x minus y, and we will have a sign difference. So that's not a problem. Yeah. Uh, yeah, you are going to have a sign difference, and it is going to come out correctly when you do something like that. So what we have is this right now. It's just variable. It's just variable change. Now we can take off the row, and we have Yeah, so this can be written as minus 1 by this is what I actually wanted to say. We don't get rid of r vector minus vector. Now the reason is, for example, cost is minus 1 and we have this is an even constant because if you do y minus x minus sign comes out and you have nothing. Minus of this is just this. So the same. Now you differentiate with respect to x, differentiate with respect to x, that means you're doing this. So this will just run minus and square minus x dd x plus x minus x prime minus sine x minus x prime. So this like variable rechanging, but what I wanted to do was something else. I'll redefine this as r prime, and this as r. Then what will happen is that it's with respect to this, uh, we'll get a minus sign. No, I think that's it's like variable redefinition of the price. Or if you want, you can keep this like that. Now, what you're going to do, suppose V can be written as 1 by m with a minus sign, some gradient of, some gradient of, yeah, I think this is correct, gradient of phi t. Then what we're going to have is the whole of this thing is going to come out, and we'll have rho r vector comma t is phi is equal to minus 1 by m. Dirac delta. So it is just rho comma phi r at 1 same time is equal to Dirac delta r 1 minus 1. So yeah, this is what it is. And let us check the other formula with this commutation relation itself. We have E, which is the current distance. So minus 1 by m j a r prime t j b. We have to minus r. This is equal to This was nothing but GVGB, right? This was rho R comma T, A R comma T, rho R prime T, T B R prime comma T. Now this thing itself, the definition of J. We just have to substitute this here in this J. If we take this thing using the formula rho R, I'm going to drop T now and we'll write subscript R. V A R rho R V B R plus rho R prime rho R V B R prime V A R 1 2 plus rho R prime rho R V A R V B R prime. And this is equal to, yeah, we know VA and rho R, we just found it. So that is nothing but rho R 1 by M R prime divided delta R prime minus R V R prime plus minus rho R prime 1 by M. So this, we found it just now. Uh, this is it. So when you interchange this, then the minus sign will go, and you're going to make suitable adjustments in this part also. That is what I'm doing here. V B R D delta and prime V A R plus rho R prime rho R V A R prime. Here, this calculation is long, and the idea is that we can show that phi of phi t comma phi of phi prime t is equal to 0. And we want here with the condition rho of phi prime t not equal to 0. So let's discuss the Euler equation now. So we'll get that the Euler equation is something like this. Where F is the external force acting at the point R at time t minus velocity at point R at time t dot convective derivative. This is called the t. This part is called the convective derivative. Now, if force can be written as some gradient of a pressure by rho plus, say there is an external mg force also, gravitational force. and this is along some direction. So that is the Z cap. But I'll just write this as G. Then you can substitute here to get an equation of this kind. Now, what I'm going to do is I'm going to solve the problem, assuming A, that the fluid is incompressible, that is, density is constant of time and space, and it is irrotational, that is, V can be written as the curl of V is zero. Incompressible curl of V being zero, irrotational. That means V can be written as some gradient of some phi potential field, some potential field whose derivative gives the velocity. It's these two things which we are going to assume. And we are going to solve for fluid in a fluid flowing in a fluid flowing in a uh, well in the book it's given for this thing. I'm just trying to modify an example. Let us try to solve for fluid flowing in a semicircular kind of. So fluid comes from here, goes, flows, goes away, something like this. So we have a semicircle at say some point like this, and there is a semicircular region. This is straight, flow along. The normal direction is zero. So this is our surface. The surface is determined by so this is our origin. Then r and this is the length is the radius is 1. So cos theta, sin theta with theta between pi by 2 to 3 pi by 2 and 1 minus 1 and 1 minus 1 when x is greater than 0. This is our surface. looks kind of like this. Okay. So let us start by writing uh, the continuity equation. Continuity equation is del rho by del t plus del dot j is equal to 0. J can be written as del rho by del t implies this is 0 because fluid is incompressible, this is 0 plus del dot j just becomes del dot v because rho is a constant. So we have this equation and d can be written as some uh, gradient, right? Because the fluid is irrotational. Since v is some curl of the m curl of some gradient of some this thing. So we are going to have del square phi is equal to 0. Okay. So the best way in the coordinate in which we should solve this is the best coordinate for this part of the problem is nothing but the uh, what do you say the partition coordinate, and this part the best equation to solve this equation is the plane polar coordinate. But let us try writing these boundary conditions in terms of plane polar coordinate if possible. So if we were to do that, if we were to do that in plane polar coordinate, yeah, how do I write the equation for this line? So that is going to be, so this is some r vector minus, the equation on the line will be r vector minus, uh, which is just y cap is equal to, yeah, r vector minus y cap dot y cap is 0. So that means the equation is r vector dot y cap is equal to 1. This is one equation. Or in other words, if so 5, we are going to take 5 from this. So this is 90 minus 5. That means r cos 90 minus r sin phi is equal to 0. In other words, this is the equation. It's equal to 1, sorry. Yeah. R cos r sin phi is equal to 1. And similarly, for this part, we are going to have, this is phi again. So this is going to be, yeah, this is going to be, so if this is r, this is the angle between those vectors. And this is going to be, um, this angle is going to be, just take r vector minus, that is plus minus of minus like that, dot or y cap or minus y cap is 0. R dot y cap is equal to 1 minus 1. And r vector dot y cap is the angle, and this is theta. So we r cos theta minus 1. And theta is nothing but theta is nothing but in terms of is to the 90 degree minus phi should be taken from this side. So I'll have to take this phi to be 90, 90, 90 plus so phi is 93 3 pi by 2 plus theta is equal to pi. So theta is in terms of pi, 3 pi by 2 plus 3 pi by 2. Therefore, cos of theta is equal to cos of pi minus 3 pi by 2. This is minus sin. We're going to get the same equation. Yeah, because if you have phi to be minus phi, you're going to get this. Solve it. This is fine. So let us just solve the equation. Del square can be written as 1 by r del r r. I'll just write it directly. Del r del r plus del square r plus. I'm writing this equation del square r plus 1 by r of del r plus and then square equal to 0. Now you are going to do the separation of variable r of theta. Yeah, like theta. Theta. So this will change into del square r. So 1 by r del square r del r. And after multiplying r square, I'm going to have r square here, r here, and 1 by pi. Since this is a function of only r, this is only a function of theta, let's take this to be minus n squared, and let's take this to be n. So if this is minus n square, we have pi of pi is simple, it is nothing but a to the power I and pi and b to the power minus I and pi. Okay. And where this part is m square, and this is minus m square. So if that is minus m square, that means r squared by r equals 0. Now, what you're going to do is choose r of r to be r to the power n. Then what you're going to have is r square by r to the power n. It's going to have n, the first derivative will give n to n minus 1, r n minus 2 by r to the power n. Yeah. plus plus r by r, which is to the power n times r by r, which is n minus 1. As n square equal to 0. You see all these cancels, and we are going to get n square minus 2 or n square minus 10 plus n minus n square is equal to 0. That is n square minus n square equals 0. So n is equal to plus minus n. Therefore, r of r is equal to, so a and b are already used, c r to the power n plus b r to the power minus n. So we have, so phi is equal to c r to the power n plus b r to the power minus n into e a to the power I am phi plus b to the power minus I am phi. Now the boundary conditions are that the boundary conditions are velocity normal. The first thing is that in infinity the velocity should go to 0. Okay, we don't want that. We want to have finite energy. So velocity at del r f phi. This will give you velocity, the minus and the m minus 1 by m del r phi at r tends to infinity should be equal to 0. This will already tell you that the function should be detained in r. So this is this m is mass. This m is mass. This m is not the same as this m. That's why I'm writing it as particular. So del r of this thing should be at infinity should be 0, and that is 0 only for this part, which implies that c is equal to 0. So you're going to have pi as b r to the power minus n, b e to the power minus 5 is b e to the power minus n. Now comes the difficult part, saying that velocity at the surface is 0. So the surface, so you just have to find the velocity for that, right? So which is given by minus 1 by n del I g. So we just look at something which is so d and the term in polar coordinates 1 by m del r r phi plus 1 by r del del r phi. This is going to be minus 1 by m. Okay. this mass. So you have to this mass, this one is mass. So del R, that is B minus B r to the power minus 1 minus 1. A to the power minus 1 plus B to the power minus 1 plus 1 by R B at minus 1. I need to differentiate this I times L A to the power minus 1 B I to the power minus 1 minus B by M R minus minus 1 and also I into the power minus B into the power minus minus 7 to the power minus 7. So this is velocity. This is pi cap. This is 1 cap. This is pi cap. This is pi cap. Minus pi cap. Okay. Now B at are tending to infinity should be 0, so we already put that. B at um, uh, V at so velocity at okay, V dot y cap should be 0 for the cos theta. V should be 0 for V of y cap is the V of uh, V of R, the component of VR should be 0 for theta. The R component of V should be 0 for theta greater than 5 greater than 5 by 2 and R equal to 1. So we're going to put that condition. So why is that condition true? Because we don't want any velocity in the R direction. It is the normal direction here. So if we do that, we will put this and I, I will just want to happen. So minus a to the power I will take this to be 5 is b to the power minus I will 5. Now m is an integer, so this will have I of 5 is just 1 and is also 1. We will have a is equal to minus b. So a is done. Similarly, we can uh, at pi by 2 also it should be the same thing, greater or equal to pi by 2. Pi by 2 also the same story should repeat. And e to the power I and pi by 2, this is just uh, it will be just I plus b is just going to be plus I only. That's going to be minus I. Well, it's a special case, it seems. But whatever, we have gotten that a is equal to minus b, and that should be correct. So if we put that, we're going to get b is equal to so a r if you are plus plus minus plus equals minus b. After you are so we should put more conditions. We have not put the conditions that b at we at this positions, we at these parts are non-zero. So that surface will be r cos theta, r sin theta, r sin phi is equal to 1. And we're going to have to put that r sin phi is equal to 1. So, yeah. So b at r equal to 1 by sin phi, and phi between pi by 2 to minus pi by 2 should be v of should be for v or as a whole should be 0. As v of theta should be 0 and v of r should be 0. Well, this is better if we change. Now what we've got to do is change phi cap and r cap and r and write this term. Let's calculate that. So that is a bit tedious job, but it's doable. It's not that it's not doable, but it is a bit difficult. Anyway, with this, we'll end this session. Thank you. Okay, I'll stop recording.